So indeed, my title today is Mean Field Games on Unbounded Networks and the Graphon MFG Equations. And this is work with Huang Gao, my current postdoctoral research fellow and former student, and Minyi Huang, professor at Carleton University in Ottawa, and a former student of Roland Mallarmé, who's in the audience, and myself. So the program is some propaganda, as if you need it, for mean field games, which have been beautifully presented in the PDE context in several talks at this meeting. Just a slightly different perspective and to introduce a key feature. And then we're going to introduce the motivation for considering what is effectively a new mathematical theory, effectively, of complex networks, which I hope, in all modesty, might be relevant to the study of crowds, and for which we are developing a control theory. So then we're going to specifically present our initial results. This is initial because we're starting in all of this on Graphon control systems, Graphon mean field games, and we finish off with a linear quadratic Gaussian example. So, there are essentially 4 parts to this talk, and I'll try to step through them efficiently. So where Minyi, Roland, and myself started with the stochastic models for the many-player game setup is given here. I hope these slides are not too faint for you to see. The images don't look as vivid here as they do on my laptop screen. The notion is that one has got a large number of agents, as you've heard in the talks up until now in the meeting, and with states here denoted Zi, and that the dynamics of each agent are given by a averaged deterministic drift part and a stochastic term, the diffusion term, where one has here an average of influences over the other agents. And what I want to draw your attention to right at the start is the fact here that one has a flat average 1 over n. Okay? So that one's averaging over the influences of all the other agents. Notice here the indices for this is the ith agent. Its state appears in each of these functions as they are averaged over the states of the other agents. And here one has the state of a major agent, which stays as a order 1 entity as the number of agents goes to infinity of what we call minor agents. And you'll notice here the ones that the ith state appears in the intensity term on the Brownian increments, and we're averaging again over the states of the other agents. Similarly, in the loss functions, or the performance functions, for each agent, this is what makes it a game, of course, that the individuals have performance functions attached to themselves, so they have their individual interests. Here we have for the order 1 major agent, its performance function, which is this expectation of the integral of the average of the cost rate functions of the influences of the other agents. And here we have the minor agents, the agents who are asymptotically negligible, whose cost functions depend upon the major agent, and of course are averaged over the other agents. So Now, the underlying, we have a complete filtered probability space, which is generated by the mutually independent initial conditions and the independent of the independent Brownian motions on each of the agents. Right, now, the way that we go to the limit here is to consider a McKean-Vlasov equation where the trajectory of a generic particle is governed by, so we're going to, what's happening here is we're going to the limit, we're averaging over the other generic agents, along the generic paths of the system. And so the average turns into here an integral in the limit against the measure governing the generic path of an agent. So what we have here is a extended Markov process in the sense that a solution is not a single trajectory, but it's a pair. Namely, we have the trajectory of a generic agent, a typical agent, and the measure governing the agent. So now I'll make a remark at this point that it's because we come in with a formulation like this that it appears that we join up with the formulation that Guillaume Mazzanti presented earlier in the conference. So, so then similarly, the infinite population limit costs are written in this form of an integral against the measure of a generic agent. So there are one of the key features of mean field games is that the strategies of the individual agents depend only on their local information. So this is highly motivated from the point of view of large-scale systems, because it means that not only is it the case that each agent you'll see, not only is it the case that each agent is restricted in its information pattern to its own state and deterministic quantities which it can compute, but it's of no value for it to do anything else. This is a key feature. So this simply spells out the fact that the local information is the trajectory of the individual agent, and that there is indeed also a global population information set. Now, the notion of equilibrium which we're using, which is basic to, again, all of the previous mean field game presentations, and which I don't want to overlap with those because they were complete and elegant in the partial differential equation framework which was being presented and used. Here we've got the notion of a Nash equilibrium is, as I'm sure you're familiar with, that a unilateral move by a single agent yields no gain when everybody is using those strategies. So formally, a set of controls adapted to the local information set generates a Nash equilibrium with respect to the individual performance functions when the loss incurred to the ith agent cannot be reduced if it makes a unilateral move away from the prescribed set of control. Notice here that this is actually in a strong form because we're not just allowing the delinquent agent or the unilateral agent to move generally with respect to its own information set, but we actually here allow it to make any move with respect to all of the possible information which is available. Right, so now, so this is the famous picture of a zero-sum equilibrium between, in a zero-sum game, the equilibrium between two players, which adds nothing technically to this talk, except to give you the famous image of a Nash equilibrium. So, what we actually deal with, because we're very interested in approximations, is an epsilon-Nash equilibrium, which is essentially, as it says, that given an epsilon, and then the strategies that the Nash equilibrium holds up to epsilon. Namely, if you make a unilateral move, you can gain up to epsilon's worth improvement of your performance. Okay, so the fundamental partial differential equations, which you, which as I've said before, you've seen in this meeting, is that going to the limit, so assuming all the limits exist, then, then the generic agent's best response strategy is generated by the solution to a McKean-Vlasov Hamilton-Jacobi-Bellman equation, displayed here, where the measure for the generic agent is generated by a Fokker-Planck McKean-Vlasov Fokker-Planck equation, Fokker-Planck-Kolmogorov equation, displayed here. And as was clearly emphasized by Martino Bardi, the Hamilton-Jacobi-Bellman equation is propagated backwards in time, and the Fokker-Planck equation is generated forwards in time. And this is equivalent to the stochastic differential equation describing the behavior of an individual agent subject to the controls. Now, the key point here, again, which has been mentioned before, but these ideas are definitely worth saying more than twice, is that a large-scale game problem, which is intractable, game theory problems are intractable when you've got 3 agents or 4 agents, so that's what large-scale means there, but the game theory problems that we're thinking of are of the order of 200,000, 300,000, or millions of players, then that's turned into a stochastic control problem. Because at the equilibrium, which of course we haven't yet proved exists, the individual agent is playing against the mass. What it sees is going to be this deterministic measure propagating, and it plays against that. So it's a stochastic. So the way that the sort of the magic circle is entered, the equilibrium, is that it turns a game theory problem into a stochastic control problem. And of course, the question is, does the equilibrium exist? Now, then the answer is yes. And in particular, that subject to technical conditions. Now, I attempted to spell them out in a little bit of detail here, because it's not really satisfying when somebody flaps their arms and says subject to technical conditions, which I won't make completely explicit today. So I'll make them semi-explicit. It's that for all the functions concerned, so this is a general sort of generalization, not the full details, one's assuming uniform continuity and boundedness on all the functions and their derivatives, and Lipschitz continuity with respect to controls. Okay? So we can supply the details, but I don't want to go into those here. Now, then there does indeed exist. So a unique Nash equilibrium, which is generated by the state-dependent control of a generic agent, and it will depend on the solution equilibrium measure. So furthermore, we have the epsilon-Nash property. For every epsilon, there will exist a population size n epsilon, such that for all population sizes greater than that, if one plays the infinite population strategy in the finite population setting, you're within epsilon of an equilibrium. Okay, now the reason that we think that we consider this to be very important is that the application of MFG theory in a quote practical situation, or on a problem with a large number of agents, is hugely simplified by this fact. So if one's got 300,000 players, instead of trying to solve a 300,000 player game problem, one goes to infinity, one solves the, let's say if it's a mechanical situation, one might have 2 pairs of 6 entry PDEs, and so one's going to be solving 12 PDEs as against 300,000 PDEs, assuming that an equilibrium even existed. So this short circuits, this runs around the complexity. So that, of course, it's a part of the limit theory of mean field games, but it's also the crucial feature of its application. So the outline of the proof, so I must watch time here, is that how does it work? Well, you restrict the Lipschitz constants so that a Banach contraction argument functions. So the key ideas here are that, and I'll rely on the chair to give me the famous 10 minutes, 5 minutes, and 3 minutes flash. Okay, so the key ideas is that we have a Nash equilibrium, so to a stochastic control, which is generated by a solution to a stochastic control problem. We have dynamic regeneration, namely that equilibrium is dynamically pushed forwards, and there's a drastic simplification in terms of complexity. Okay, now, now the point is that for many reasons, one wants to apply, now this is the most exciting part, whether this, the simulation works. So we're through the hardest part of the talk. Okay, so so here we have one of these familiar schooling pictures where we've got a school of interrelating, actually they're sardines. So they're interacting with each other. There's some sort of equilibrium. And here comes a major player, okay, that's coming through, that you don't want to mess with him or it. Right. Now, the point is, I don't think that MFG theory straight off applies in this situation. Because, firstly, the sardines relating to their neighbors, they're not taking a 1 over n average. You can't imagine that they're seeing a flat law of large numbers average taking place. And also, I don't think that there's one measure for which a single kernel can be seen to be integrating to get the behavior. Now, this rather cheesy picture here brings us to networks, which are ubiquitous. So the point is, how are we going to deal with local effects in large-scale systems? How can we apply mean field games when we have local effects, but they ripple out from each agent? So locally you see your neighboring agents, but in fact you're interacting with everybody through this. Can we apply mean field games to it? Well, this challenge comes up obviously in networks, which are everywhere today, power grids, epidemic models, brain networks, social networks, okay, and conceivably crowds. So we're going to consider networks with large numbers of nodes, in principle millions or billions, complex connections, which are asymptotically dense. This is a technical point, but locally, in the theory we're using at this point, you're going to have an arbitrarily large number of neighbors, but those connections do not stretch necessarily over the whole network. But the locally finite problem will be tackled depending upon the advances in the theory by those who are working on it and our capacity to understand that. Right, now what's a graphon? So a graphon is a startlingly simple idea for dealing with complex graphs. So, and when I say startlingly simple, this is the image. You have a graph, you have its adjacency matrix, and you turn that into its pixel picture in the obvious way. So here we've got 1 over n, of course, partitions along the axes. So we have the pixel picture for a given indexing of the nodes. Now, take this to the limit, you see, as we fill in more and more elements as we run along a sequence of graphs, which could be growing, they could be nested or may not be, then in the limit, you see, you might conceive that you have some kind of dense image, some kind of function at the end. So now, technically, a graphon is simply a bounded symmetric Lebesgue measurable function displayed here. And in the simplest case that we deal with, the values are between 0 and 1, corresponding to intensities. Okay, so you could imagine it being only 0 and 1, but if the strength of the connection varies, as in many problems of interest, then you take values in 0, 1, or even between -1 and 1. Now, the theory of graphons was developed basically by a combinatorics group centered on Budapest and the Microsoft research group in Seattle. And there's a marvelous exposition by one of the architects of the subject, Laszlo Lovic, Large Networks and Graph Limits, published by the American Math Society, reporting the state of the subject in 2012. The idea, now the point is that the space is given a norm, which is called the cut norm, which is given by this definition that you're integrating over the unit square. You've got the modulus here on the outside, and one's then taking the supremum over subsets M and T, the measurable subsets, of course, of the unit interval. Then the cut metric is that one then infimizes this. Here you've got a supremum, then you infimize over the indexing of the nodes. Now, this infimum makes things difficult to handle, but in fact, we can, in many situations, there's a settled indexing of the nodes, which means we don't have to worry about that, which is a great relief. Then there's a relationship. Now, I should mention that the cut metric is a direct generalization of the notion of a cut metric in normal graph theory. And it has some amazing properties. For instance, if you want to get like the density of triangles, which might be important in crowds, if groups of 3 were important, you simply integrate the Graphon function in this way, this triple integral, over the unit square. And then here I should have finished with an X, an error which I'll correct next time I'm near the board. So now the point is that in this metric, which is which is bounded above by the L2 metric and bounded below, subject to mild conditions by the L2 metric as well, that the space is compact. So this means that with any infinite sequence of graphs mapped into the unit square in this way, using the cut metric, one has convergent subsequences. And in well-defined situations, these will actually be unique. So now suddenly the world of complex networks is suddenly mathematically under control. It's turned into a part of functional analysis. So then off we go. We can now actually we've got here actually, we go from the norm to a metric, the properties which I've just described. And now we have an operator. You see we have an operator from L2 to L2. We can convolve. We've got an infinitesimal generator. We can now define differential equations where the states are going to be L2 functions on the unit interval. So now what I'm going to do, how much time do I have exactly left? Okay. So then we'll try to do 5 minutes for control theory and 5 for mean field games. So to step through perhaps the control theory, we can actually take linear control problems. Here's the picture. You see here's the finite dimensional system. Here's halfway infinity. You see here you've got functions on the pixel elements, and then you go to the well-defined L2 limit. And then one can actually solve linear control problems in the sense of, now it's just turned into classical infinite dimensional linear control theory. So we've taken problems on sequences of arbitrary complex networks and turned it into linear control theory, you see. So then we can solve, and I'm going to step through this now quickly. We have here the notion of controllability, if you can steer from any state to any state. We can define a Gramian in analogy with the finite dimensional situation. Here we require uniform positive definiteness for state-to-state controllability. Again, classical infinite dimensional linear control theory. And then, in fact, we get our control methodology. This is clearly mean field games driven, because you start with something very complicated. You step to its limiting smooth infinity object. You solve your problem there, and then you apply the infinite, so to speak, the infinite limit, simple control law in your complex finite situation. And it works in the sense that we can prove, and I'm going to have to step through this, you can actually prove the convergence that if you've got a control law designed for the infinite system, then, and if you sample it and apply it to the finite system, then you have approximations, which of course will get better. This is the terminal state approximation, which will get better as n goes to infinity, namely as the network converges on the limit Graphon. Okay, so now I'm going to step through this, and I apologize for doing this quickly. So these are simulations where a smooth Graphon is used to sampled. You generate a network, and then for using a control which is generated analytically on the Graphon limit and applied to sampled and applied to the complex network, then in fact one can steer the states of the nodes in a very precise way. And of course this gets more precise as the number of nodes increases. Okay, let's get through to, and this works for LQG theory as well. So you see here's the smooth Graphon, and here's a network of 160 nodes which is converging to the Graphon in the cut metric sense which I've described before. Right, and the control laws are computed for the smooth limiting object, not for the complicated sampled object of the networks. See, when you've got 500,000 nodes here, obviously this is the simpler thing to use. Now, let's go to mean field games. Now, the point is, as I said, that I don't think that the motivation here is that the flat 1 over n averaging, which appears throughout mean field games, and the single measure, the single generic agent measure which appears, doesn't describe a situation where, for instance, in this picture of airport densities, you've got a different characteristics at the different clusters of nodes, which are then interacting with each other over a very complex network. So, so here is a diagrammatic representation where you have a sequence of clusters which contain a very large number of agents, where there's a large number of agents are communicating with each other over a complex network. See, so we've now got those we have now these two infinities running. Okay, the infinity locally and the infinity of the network, or in the limit. So that we can now go to a direct generalization of the mean field game partial differential equation pair that you saw earlier, and of which you're familiar with from in this meeting. So now you see that the dynamics at the dynamics and the costs, the dynamics here at the generic node alpha in its cluster will in fact be a function now averaged over the Graphon. So the picture here is that you're sitting at the agent alpha in its cluster, which has now turned into a point. So you've now got an infinite number of agents at a point, and those are communicating with the infinite number of agents at every other node. And so here you see, if you strip away the 0-1 integral over the Graphon, with the Graphon waiting here, then we've just simply got our old McKean-Vlasov integral. We'll just be integrating. Here this is R because it's scalar states for simplicity. You see, if I had x alpha, the control u alpha, and then x beta here would then be integrating with respect to the measure at, just set beta equals to alpha, so there's just one node. See, that if I have here mu alpha, dx alpha, and then I'm integrating over this free variable, then I've got the McKean-Vlasov integral that gave us the limit population before. But now I have another integral, which is that I do that McKean-Vlasov integration at each node beta over the network, and the weighting between the alpha node and the beta node is given by the Graphon function G alpha beta. Okay, so I wonder if I dare try to just use the chalk, and so the picture, what it comes down to is that so here we've got our unit square. Here we've got our Graphon function, a point here being the intensity of the connections between the alpha and the beta node. If I'm sitting here at the alpha node, then what I'm doing is, and I've got here my Graphon intensity, is that at each of the points here, there'll be sitting a measure which describes the behavior of the generic agents at the beta node in the infinite network. So then, and then I integrate that at alpha, I integrate over those measures, which are going to be distinct in general, at each node. So this integration here gives me the dynamics, similarly for the cost. Now, for the LQG example, then we have an existence theory, which is a generalization of the methods that give us the existence and uniqueness in the classical MFG case. And we've almost got a complete, we've almost got, let me go the right way, we've almost got a full epsilon-Nash equilibrium result. So this is work with Mean Field Huang. The existence and uniqueness was presented at the CDC last year. The Nash equilibrium, we hope, will be accepted for the CDC this year, and we're working on the overall paper. Right, so the theorems read the same. You see, it's like declaring Lyapunov stability or declaring optimality. See, there's no exciting new information here, except there is this, for me, exciting new setting. But it's a direct generalization. And it's worth mentioning that you retrieve the classical case by taking a flat graphon. What's happened to the classical case? Well, you just set the graphon equal to a flat level, okay? And then you retrieve the classical case. Right, so now for the, here we, how many more minutes?
5.
Including questions?
No.
Okay, so in order that we get a question, I'll say that, you see, here's the LQG problem, here's the LQG case. Here is the finite averaging, okay? Here we have the individual's costs. Incidentally, this business of following the crowd was the original problem that Mini and Roland and I considered in our first LQG MFG paper. So now let's couple these the clusters by the uniform attachment graph, whose graphon is given by 1 minus max alpha beta. Okay, so then we have the individual agent's cost. You see, it looks the same as before, except that then the last 2 slides of the talk are here. Here's the individual agent's dynamics. Here's the class function, looks the same as before. But each agent is dealing with Z alpha. Okay, it's tracking Z alpha, which in fact you see is going to be a weighted mean of the other agents over the network. So here the Z alpha here is the graphon weighted means of all the other agents at the other over the network. Then the control equations look the same as they did in the classical case, except that the S alpha equation is driven by V alpha, which is the graphon mean over the whole network, not just the mean with respect to one measure, but is a mean with respect to all of the measures of the agents to which it's connected over the network with intensity given by the graphon. So that's the mean state process. Okay, so that's it. So what we've done here is mean field games, the introduction of the notion of a graphon, indicated mean field graphon control, and then given the, well, I'd like to think it's a natural generalization of classical mean field game theory to mean field game theory on graphons. And that's the LQG example to prove it works. Thank you.